Okay students, so in the previous class we discussed about isomers. So we discussed mainly focused on structural isomers, right? So in this class we can more focus on stereoisomers. So as I discussed in the previous class, stereoisomers means no, you will only see a change in spatial arrangement of atoms. Okay, this is not just an interesting chemistry law. So let us go through it. First of all, let me start with how we can representation of organic molecules. So how can you represent such molecule which have different spatial arrangement? So how can you understand that? No, they have different spatial arrangement like that. So let me start with the simplest one. First one, I can tell you there are three representations that I am discussing here. First one, flying wedge representation. This is one of the simplest method where now let me discuss the simplest one, that is methane. We know methane having a tetrahedral structure, which means no, they are not planar. Methane is not planar, not in a plane. Okay, so we can represent this methane molecule using this wedge dash representation. Sorry, it's now flying wedge representation. Where now you will see this thick line, or we will say wedge line, that represent now here hydrogen is there, that represents that particular hydrogen atom. No, this carbon attached to this carbon atom. So this carbon attached to this hydrogen atom. That hydrogen atom is coming towards you. So we can imagine it is above the plane like this. No, it's coming towards you. It's above the plane. So not in the plane. This thick line represent no. This hydrogen is coming towards you. It's above the plane. A broken line, a dashed line you can see here. That hydrogen represents no, it's going away from you. That means no, you can imagine inwards going away. Okay, and the two hydrogen no, simple continuous line that represent no, these two hydrogen are in the plane. You can represent in the board. Okay, so this is the way, one of the way you can represent a three-dimensional structure. Well, what's the point here? You will know it's all about spatial. So normally you require no three dimension to represent. So only way now we can represent something now such representation. Like this hydrogen now, which is now having a thick line that coming towards you, towards the observer, and this hydrogen away from the observer, it's going backwards. And here now, generally the thick part now, this is the lower end and this is the upper end. So this part going towards the substituent, and now the thin line, this is the thick part and this is the thin part, right? Thin part now attached with this the carbon atom. So that's the way we generally represent, one of the representation of flying wedge representation. Okay, so let us discuss one more cases where no ethane. Ethane stands for not two carbon is there, and we normally write like this CH3 right. This is the way normally we represent. This is methane for you. But now it's actually observed that this methane molecule is no, sorry, ethane molecule is not planar, which means no, one particular hydrogen now which is you cannot represent in the plane or one or two. So that suggests it's not a planar compound. So how can we represent? Now using flying words represent, we can represent it by now like this, where one carbon and two carbon bond I represent like this. Now where you will see Get line hydrogen here. Okay, and next similarly this carbon also have hydrogen, which I represent like this. Okay, then hydrogen, similarly a dashed line hydrogen here, a dashed line here, and normal line, that is CH bond, that is now represented here. So this is CH3 that is ethane for you. So what's the speciality that you saw here? This is, we can say, a staggered conformation. Let me write the other one also. Let me draw it, because that will be easier for you to understand. So let me draw here carbon carbon single bond. This time the thick hydrogen atom here, and similarly hydrogen atom here. Then this two hydrogen which is in the plane, and there is a hydrogen here, hydrogen here. So this we will say a eclipsed conformation. So we represent now two spatial arrangement of this ethane molecule. That one is called staggered conformation, other we call eclipsed conformation. So what do you mean by conformation? Conformation means now we just rotating we just rotating one part of the molecule with respect to other part, no, based on the carbon carbon single bond. So conformation stands for only for saturated compound where carbon carbon single bond is required. For double bonded and triple bond compounds, this conformation is not there. So what does it mean? Here, look at here, this part is not same here. Okay, this hydrogen, and this part is same. What I did now, I just rotated this part with respect to this carbon carbon single bond. So this time this hydrogen was here. Now you can imagine this is spatial. So many hydrogen atom. Now this can be here. That time this will be here. This will be here. So at each point now you can make so many different spatial arrangement. Okay, this you can interchange and now here and there so many carbon hydrogen bonds you can draw if you start drawing, which means the point is it's all about three-dimensional, it is spatial, so many arrangements are possible, or we will say conformations are possible. So what doing in conformation, we just now fixing one part, and with respect to a carbon carbon single bond we just rotating the molecule, rotating this part. So now here you will see these are, we will say, two extreme cases. One is now staggered conformation, where now you talk about the hydrogen which is coming towards you, the hydrogen which is coming towards you, which is now almost at a very far distance, not nearer. Which means now this electron-electron repulsion will be minimum in the staggered conformation. Okay, in the eclipse conformation you will see the two hydrogen atom which is now coming towards you are at the same side, which means now there is most possibility of electron-electron cloud repulsion. So we will say eclipsed conformation is the least stable, while staggered conformation is the most stable way of conformation. In between that, infinite conformation is possible. Look at what's the main difference here. Here now the hydrogen was the dashed line hydrogen is here. It is here. Now this thick lines are coming here, and this hydrogen in the plane is coming here. So here now you will observe the maximum repulsion between the hydrogens of nearer carbon atom, and here you will see a minimum repulsion that we call staggered conformation. Then in between this, infinite number of conformation you can imagine. This now you can put just rotating here and there, this hydrogen here, like now it's spatial. So infinite number of conformation are possible. But in between these extreme cases, one conformation with the most stable arrangement and next conformation least stable. So now that why the conformation, for representing conformation, we can use this flying birds representation, which is one of the way. Okay, so think like that. That's how about flying birds representation. Next case, now this is Soho's projection formula. Second case, Soho's projection formula. Now this is interesting representation where now we represent, again I am talking about ethane CH3 CH3, okay, CH3 CH3. This is more useful now, especially to explain conformation. So this is actually a carbon atom, this is also actually a carbon atom. So the carbon-carbon bond I just expressed in an elongated way, and I'm just drawing a inverted Y. Now you can imagine this is a Y, and now this should be straight. Okay, this is now a inverted Y like. Okay, this is hydrogen, and this is hydrogen. Okay, now next one is also I am representing in a inverted Y. This is hydrogen, this is hydrogen, this is hydrogen. Now let me represent another way. A carbon-carbon long elongated bond. Okay, this part I fixed. This is again a inverted Y. No, this time this is now normal Y. Sorry, this should be normal Y. Here it is normal Y. Here is again now it's inverted Y. Okay, so in this type of representation, I will call this is a staggered conformation of ethane. This I will call eclipsed conformation. So what's the difference between these two? Now here you will see the hydrogen between the two carbon atoms are almost no as far as possible. There is no repulsion between the hydrogen is very less. That why you can say this conformation that's actually for ethane. This is carbon, three hydrogen, and now that is almost very far from each other, which means no minimum repulsion. So this is the stable conformation as far as the most stable conformation as far as the ethane is concerned. Okay, but look at here now I just fixed this part and just rotating the other parts. So infinite number of conformations are possible. We just now putting here, hydrogen here, like that. So many infinite. Just a marginal difference get you another conformation. So like that, infinite conformations are possible. But here now, this is the case. Now I just represent as now like this inverted Y, where now you will see maximum repulsion is experienced between the nearer hydrogen atom. You cannot go beyond that because repulsion will be highest. Again, now it's so another extreme case is not possible. Not we can draw. So the point is in an eclipsed conformation we express the getting the maximum repulsion, electron repulsion. Hence now this will be the least stable conformation. Now this is not the part where discussing about conformation. Still we have a lot to discuss about conformation. This is not just learn the representation. How we can represent a three-dimensional structure using this. Now flying wedge representation. So who's the next one? So what good about Soho's now? It is more give you information related to the conformation. If you want an idea about the conformation, this representation gives you more idea, because now here you will see now hydrogen is at a maximum distance, which means now it will be stable. So that's all about a Soho's projection. Where remember carbon hydrogen is always maintain a bond angle of 120 degree. That's how we generally represent a Soho's projection formula. Okay. Similarly, the third one, that is Newman projection formula. Newman projection formula. 2n is not there, sorry. Newman projection formula. So this is the case now. Still, this is not for the study of conformation. So that's the way you can imagine Newman projection formula and Sohor's projection formula. There now, interestingly, we represent one carbon. Again, remember this is CH3. For ethane I am discussing. One carbon I represented with a circle, and one carbon now it is there at the center. Just it is represented as a dot. Okay, so one circle which is a carbon and one dot again it's a carbon. So here now we actually representing a, this is hydrogen, this is hydrogen, this is hydrogen. Okay, CH3, one of the CH3 is done. Next case now I am drawing okay, the other CH3 part. This is hydrogen, this is hydrogen, this is hydrogen. While you are drawing, now always maintain HCH bond angle 120 degree. That's the way we represent Newman and as well as Sohor's. Okay, should be like 120 degree to each other. Okay, you imagine a line like this, it has to be 120. So this represent, I can say this is staggered conformation, and this I will say this is eclipsed. Next one is eclipsed, where now again one of the carbon atom is a circle. Next one I am drawing like this, where now you can draw this one part that is fixed, that is this part I fixed. Okay, you can say that's the nearer carbon atom, so that is fixed. The other hydrogen atom, other CH3 part, now I just rotated a possible manner, so that now there is a one case will come where this hydrogen atom are most closer. Okay, it is most closer to each other. Okay, that's the case where now you experience highest electron repulsion. Hence, this is now we can say eclipsed conformation. Now, this should also maintain a 120 angle. So, just careful about that. So, Okay, we have to make sure that is no a 120 angle is maintained. So now this is the case where staggered conformation, you can see hydrogen now are far apart as possible, which means no minimum repulsion. But in the case of a eclipsed conformation, you will see they experience highest nuclear repulsion. Sorry, highest electron repulsion. So that suggests you no there are two types of conformation that represent staggered and eclipse conformation. In between, the infinite number of conformations are possible, which no varying degree of repulsion. One is most stable, that is staggered. One is least stable, that is no eclipsed. So these two representation generally is actually good for this to explain this conformation. Okay, so learn this. Now, there is one more representation is there that we call Fisher projection. Remember, this is the fourth one. Now, this is not we are discussing now because this is more related to the optical isomers. There, so lots of point is there to discuss. Like chiral carbon is there. Talk about stereoisomers, which are looks like a mirror images, but difference only in their rotation about the plane polarized light. So we need lots of discussion. What is chiral? What is plane polarized light? Everything. So there I will represent now what is this Fisher projection formula is all about. Remember, this is more related to the case in the optical isomers. This also one of the representation of a stereoisomer. So anyway, during that point I discussed this as well. Another way of representation that is called Fisher projection formula in the to explain optical isomers. So we need a good discussion what is optical isomers is all about. So there I will discuss this point. Okay. Now there's one more point. Now we can imagine how we can convert a Sohorst uh, to Newman and Newman to Sohorst. So just imagine. Let me draw that again. This time. This is we will say staggered. Now let us imagine how we can convert this staggered into Sohorst into Newman projection. Here now, remember this is carbon, right? Only difference is main difference will come where we representing this carbon atom in a circle in a Newman projection formula. So what you need to do, you fix this part here. I didn't do anything. I didn't make any change here. I just fixed that part. Okay. In the next part, I just converted this part into a circle. I converted that part into a circle. Okay. So now it didn't make that much change here. Instead of this carbon, now we in Newman projection we putting a circle, right? So I just put a circle, and the orientation should be similar. Here it's here, here it's here, and here it's here. Okay. So that's the way I represent it. Okay. Now, you just imagine what you are doing. This is one of the carbon part. So we actually converting what Sohorst to Newman. That's what we are doing here. Converting Sohorst to Newman conversion. So first I drawn the Sohorst projection formula. Remember these all are hydrogen. Hope you remember that. Talking about ethane again. So what's the change I made here now? This is one of the CH3 part. I didn't change by any means. I put it here. This part now, I just converted that carbon into a circle because that's the way we represent in the Newman projection. So that carbon and the hydrogen I expressed now in a normal way. Now it's all about now next part, just elongate or push this part to here. Yes, I am pushing this part here, and so that now I get the Newman projection formula for this staggered. This is staggered representation, right? This is staggered conformation. So I am getting a staggered conformation in the Newman projection formula. So it will be a circle will be there and a normal CH3 part that is here. Now when I push here means now this will come here, this will come here, and that will come here. So this is the way I can convert the this Sohor's projection formula into Newman. Okay. So what I did, first I drew the normal conformation, that is not staggered conformation I drawn. Then I converted this part now where this is a carbon atom, so I represent with the circle, and all other hydrogen remaining, hydrogen bonding will be same. And the next part now what I did, I just pushed this man here, I just pushed this part to here, so that now you are actually getting a Newman projection formula corresponding to the staggered. Similarly, if you do, you will get eclipse as well. Okay. Now just think the reverse manner. Reverse manner is also there. What you need to do here now, the one part you have to bring it back. You pull just now the way we did now the conversion of Sohor's to into Newman. You can convert the back side as well. This time Newman to Sohor's. What's the difference? You just bringing back one part of CH3 backwards, other part will remain there. Then it will be like this with a circle, and that circle should be converted into a normal line formula. So that will be the main difference. What I did, I pushed one part backwards. If I now push this part, CH3 part backwards, it will be like this. I push one part backwards, and we represent like a carbon-carbon bond with a long elongated bonds in a Sohor's projection formula. So I just push one CH3 part backwards. You imagine you are picking this part. Okay, this is one hydrogen, this is one hydrogen, this is one hydrogen. So you just bringing that backwards. Rest will be there. It will be there. Okay, and that I bring backwards. Now you will get a formula something like this. Okay, exactly like this. Then you have to remove the circle and represent as normal carbon, and that CH3 part will be there. So just the reverse manner. One way you study normally, other way normal. Just there we pushed this part towards here. Here just doing pulling. When you converting Newman into this Sohor's. So that's the main difference you will observe in the this Sohor's projection and Newman projection formula. Okay, it's very important. You have to now continuously learn. I have noticed some of the students didn't check the previous video. I can understand how many students are watched who is regularly learning everything. I can understand. So please read it through. Otherwise, it will be very difficult for you to learn everything in a particular day. This now, especially students are not, we cannot able to see you, but still it's very important you have to learn. Now each day you have to learn something new. That's very important. Also read the textbooks. No. So thanks for listening today. Let us see in the next class. Okay, thank you.